lecture on saltwater intrusion, uh, how it affects the coastal aquifers. Dr. Anupama Sharma has done her PhD from University of Roorkee under Professor Deepak Kashyap. He was our former professor in our department, and she actually developed her PhD thesis is on saltwater intrusion. Uh, then she developed numerical models for saltwater intrusions. Then she joined National Institute of Hydrology as scientist, and she has now is working as scientist G. And she has really worked on many practical problems of saltwater intrusion, especially on the coastal areas of Gujarat, where the problem of saltwater intrusion was alarming. And she has been doing it for a long time, and she has a very vast experience on managing these coastal aquifers from saltwater intrusion. So now I request, we also have now today Professor Tom Bowing. He's from Rhode Island. He's a professor, and he's also working on saltwater intrusion studies at Atlantic, near Atlantic Sea. So I think this interaction will be very beneficial for all of us. Okay. So now I request Dr. Anupama to deliver this lecture. Thank you.
Mouse to this assembly.
Last day? Yes. Yes, right. Must be eager to go back home. But I hope you must be wanting to listen to my talk on coastal aquifers. How many of you have, lived in coastal area? Any of you? Okay, great. Yes, good. So, what kind of issues you feel are existing in your coastal city? You are from what place?
Odisha.
Odisha. So, what problems have you faced?
Yes,
encountered?
water quality is changing.
Water quality.
Changing, like from near my region, because my location is like 4 to 5 kilometers from coastal.
Okay.
Coastal.
So
there, water quality is different. Fluoride, more fluoride.
Okay.
And but outside that region, water quality is
So have you tried to study the coastal problems? Any exposure to the coastal problems other than the people who are already staying there? Okay, so I'll be discussing with you. Just let's open this. शायद पुराना ही है।
नहीं क्या बता रहे?
यहाँ से कुछ करना है,
कुछ करना है
मुझे बाहर नहीं लगता है। यहाँ तो पहले इधर नहीं आ रहा था, अभी खुद तो क्या भी नहीं, यहाँ से निकला।
प्रोजेक्ट नहीं हो रहा क्या बात
तो इधर आ तो गया।
ये तो हो गया लेकिन हो गया। हाँ,
अच्छा
वही।
केबल इधर इधर आए, इधर आए।
ये सब में आएगा तीनों में
तीनों।
आ गया। ये वाला नहीं है ये also come.
So I'll begin with what is the significance of coastal areas? Why do we need to have this lecture on coastal areas? Then how the coastal zones are vulnerable to different kind of hydrological problems. Then we shall discuss a little bit on the dynamics of the coastal zones. What are the regional and local concerns in the coastal areas? What are the planning elements and what kind of mathematical models we can use to manage the coastal aquifers? And then finally, we will have a small discussion on the coastal management strategies, how we can, counteract the movement of the salt water in coastal areas. So basically, can you hear me at the back?
Yes.
Nice and clear? Okay. So basically, coastal zones are unique and dynamic in nature. Why are they unique? Here, both the land and sea, they interact besides the atmosphere. So they are unique in this sense that the land, the sea and the atmosphere, they all interact. And lots of erosion is taking place. The coastline is not constant. Lots of erosion is taking place. Lots of deposition is taking place. So basically, it's a very active, it's a very active environment in terms of the biologically and geochemically, it's a very active environment, the coastal zones. And people love to live in coastal areas. Some of the most densely populated areas in the world, they are coastal regions. So here in this map, you can see the top 10 largest cities. Most of them are along the coastlines. Now, if we talk about the Indian coastline, the peninsular region, it is having around 5,400 kilometers of the coastline. The total coastline of India is 7,500 kilometers, which also includes the Andaman, Nicobar and Lakshadweep Islands. And our coastline is endowed with lots of, mangroves, coral reefs, estuaries, lagoons. And we also have the low elevation coastal zones. So what are the low elevation coastal zones? Here, the elevation of the ground surface, the land surface, is barely 10 meters above the mean sea level. And even in this region, it contains about 10% of the world's population is living in these low elevation coastal zones. And in India, we have more than 63 million people living in the low elevation coastal zones. And 250 million people are living within 50 kilometers of the coastline. So you can imagine how densely populated the region is. And the figure that I have given, 63 million people, this is an old figure. This number might have increased by now. So now these coastal zones, they are, sites for productive agriculture, specifically on the eastern coast of India, where we have the deltaic regions of the Krishna River, the Godavari River. These are very rich areas in terms of agriculture. Then we also have the industrial centers, harbors, airports, land ports, fisheries, tourism. So all these are, industries which are paving way for the socio-economic development of the country. But with the increasing population, what is happening? People are becoming more and more dependent upon the groundwater for the freshwater supply. Okay, so we do have the surface water resources, but people are turning more towards the groundwater for the freshwater supply, because groundwater is generally fresh in nature. It is generally clean. But despite the importance of the coastal zones, we face a lots of hydrological issues in terms of cyclones. Regularly, we face the problem of cyclones, storm surges, then flooding, seawater sprays. What are seawater sprays? When the ocean waves, they strike across the rocks on the beaches. What happens? The salt sprays, they get showered on the coastal beaches or the soil there, and it contaminates the soil. So this is an additional problem. And then besides that, we face the problem of salt water intrusion through the surface waters and also through the coastal porous media. So this is another huge issue that we face in the coastal zones. And finally, to top it all, we are facing the problem of sea level rise because of the looming climate change. So all these issues we face along the coastal aquifers, and that's why we need to manage the aquifers and also the surface water sources in the coastal areas. So today I'm going to focus on salt water intrusion in coastal aquifers. Basically, what is salt water intrusion? When we say coastal areas are, facing the problem of salt water ingress or salt water intrusion, what do we mean by that? It means that there is an upward or landward movement of the seawater. That is, the seawater is moving towards the landward side, and the salts in the coastal system, the water is having a higher concentration of salts in the aquifer compared to the natural background levels. So the salts in the coastal freshwater system are increasing. So this is what we mean by the saltwater intrusion phenomena. Now, this salinization of the coastal areas, it is a serious issue. Why? Because it reduces the productivity of your land and water sources. It changes the chemical composition of the natural water resources. It degrades the quality of water for domestic or industrial use and also for irrigation. Lots of fertile soil is lost because of this problem. The agricultural and the fishery industries, that is also getting affected. Health issues are coming up because of salinity problems. So basically, saltwater intrusion is causing a lot of problem and it is affecting the economic development of the country in that sense. So that is why we need to study the saltwater intrusion phenomena and how we can counteract it. So if we look at the hydrologic cycle, now this is a regular hydrologic cycle which you must have been studying till now. But what happens in the, is there a, okay.
नहीं है मिडिल स्पेस पॉइंटर
Okay. So if we look at the hydrologic cycle, this is the regular cycle that you must have been studying. But what is happening when we focus on this land and sea? Here, the sea water is in contact with the fresh water from the coastal system.
yes
So let's focus on this part more. First of all, what do we mean by fresh water? Fresh water generally means that it is having the total dissolved solids which are less than 1000 milligrams per liter. For drinking water, we might say TDS should be less than 500 milligrams per liter. For irrigation purposes, we normally use water with the TDS value of less than 2000 milligrams per liter. But seawater, it is having a TDS value of around 35,000 milligrams per liter. In some other seas, you might find a TDS more than this, but this is the average value of seawater. So basically, fresh water is having less TDS and seawater is having much more TDS compared to fresh water. So when we look at the coastal region, here we see that the density of seawater, because of the higher value of TDS, the density of seawater is around 1025 kg per meter cube. But the density of fresh water, that is 1000 kg per meter cube. So what does it mean? The seawater is heavier in nature compared to fresh water. And what happens when a heavier liquid is there along with the lighter fresh water, lighter water? It tends to, the heavier water tends to displace the lighter water. So the fresh water on this side, which is lighter in nature, it floats above the heavier salt water. Clear? And because this is heavier in nature, this salt water tends to creep inside into the freshwater system, coastal aquifer system, and it forms a sort of saltwater wedge below the freshwater lens. And on this freshwater lens, what is happening? It is having a water table gradient towards the seaside. And because of this water table gradient, we have fresh water discharging into the sea. So on this side, we have the saltwater wedge, which is creeping towards the landward side. And on this side, we have a water table gradient, which is sloping towards the sea, and the fresh water is discharging into the sea. So this is another, this was the unconfined system. Again, in the confined system, similar type of phenomena is there. But in an island setting, what is happening? In an island, the island is surrounded by sea from all the sides. So basically here we have the lens, the freshwater lens floating above the salt water. And the fresh water is discharging to the sea along the periphery of the island. Now, this was the original water table, which is sloping towards the seaside. Now, what happens when we do some kind of pumping or recharge? So, when we do pumping, what will happen to the water table? If it is not being adequately recharged, what will happen to the water table? The water table will tend to, yes, tell me, if we overexploit the aquifer, what will happen to the water table?
Go down.
It will go down. Yes. So this water table will go down. And then what will happen to this saline groundwater? Basically, they are existing in dynamic equilibrium. Okay. So when this water table goes down, this dynamic equilibrium, it is getting disturbed. And when it is getting disturbed, this tends to acquire another equilibrium position. And to balance this out, this saltwater wedge, it goes further inside into the landward side. That is, it intrudes. Okay. It intrudes into the landward coastal aquifer. So this means that here the saltwater bed was intruding only up to this distance, but once the water table has gone down because of the over exploitation of the aquifer, this saltwater bed intrudes further. So this is the pre-development scenario and this is the post-development scenario. And this means the outflow from this coastal aquifer into the sea, that is getting reduced. The discharge of the fresh water that was originally happening into the sea water, the sea is getting reduced. Now, this one was the density-driven flow. It was happening because of the lowering of the water table, and because of the high density, the sea water was intruding into the freshwater system. But what happens if we pump out the water in such a manner that the water table gradient is getting reversed? That means, suppose you have a zone of heavy pumping here. So this was the original water table. Now it was like this, and now because of the heavy pumping, this gradient is getting reversed on this side. So what is happening here then? The fresh water, it is moving towards the sea, but because of this reversal of the gradient on the seaward side, we have a movement of water from the sea towards the landward side. So this means the movement of the water is getting accelerated. The movement of the sea water is getting accelerated. So this is the gradient driven flow. This is not density driven. Now it is gradient driven. So what will happen? When the flow is gradient driven, it is becoming fast. The intrusion of the salt water into the coastal aquifer, it is becoming fast. When in the earlier case, when the water table was getting lowered and the intrusion was, occurring, it was a slow response. It might take years for the intrusion to occur. But in this case, when the gradient is reversed, it is a quicker phenomena, and within a matter of a few months or couple of years, your pumping field will be getting contaminated with saline water. And this is the multi-aquifer system. Again, this is showing the disturbed equilibrium. When we pump out the water, this kind of saltwater intrusion might be taking place. So in a multi-aquifer system, because when we are pumping from the lower aquifer, this piezometric head might be going down, and some kind of water table, lowering might take place because of seepage of the water from the top aquifer to the lower one. And again, the dynamic equilibrium is getting disturbed. So this is how a saltwater intrusion phenomena occurs in a coastal aquifer setting. But in reality, what is happening? Now, fresh water and salt water. Here we are showing with the sharp interface. But in reality, what is the real thing? The salt water and fresh water, they are not immiscible. They are miscible in nature. They get mixed. So basically here the interface is a transition zone. It is a dispersed interface. So what is happening in reality, when the salt water intrudes, it mixes with the fresh water, and a transition zone is getting developed here. And in this transition zone, what is happening? The concentration is varying from that of salt water to that of fresh water. So this is pure fresh water, this is pure salt water, and here in this transition zone, the concentration, the TDS value is varying from the concentration of seawater to that of the fresh water. And basically, because this gradient is already existing and it is moving towards the seaside, this salt water intrudes and then it goes back again towards the sea, and a sort of circular movement of water gets established for the seawater. It's okay with everyone? Now, the best example of a big transition zone is the Biscayne aquifer in Florida, where around 3 kilometers of broad transition zone is existing there. So this is how this is an example of broad transition zone, a thick transition zone, or a thick dispersed interface. So now, how do we find out what is the depth of the interface below the ground surface? So for that, we have different models, but the simplest, relationship, just a thumb rule, is by using the Darwin-Husband relationship. If you look at this, coastal aquifer setting, this is your water table, this is your sea level, and here we have the freshwater saltwater interface. And here we are assuming that it is a sharp interface. It is not a dispersed interface. It is a sharp interface. So if we look at this point here, now here it is at equilibrium, hydrostatic equilibrium. So what will happen? At this point, the pressure, because of this column and because of the sea level column, it is equal. So if we equate these two, H plus Z into this rho into G, we finally get this formula for Z. Now what is Z? Z is the depth of the interface below the mean sea level, and H is your height of the water table above the mean sea level. Fine. This is your height of the water table above the mean sea level, and Z is your depth of the interface below the mean sea level. So if we want to equate the pressure at this point, what will we do? We will say H plus Z. Fine. This is your water column, and this equates with the value of the pressure because of the sea water column. So finally, if we solve this equation, simple equation, we get the value of Z as rho F. Now what is rho F? This is your density of fresh water, and rho S is your density of salt water from the sea, and H is your height of the water table above the mean sea level. So if we take the standard values of rho F and rho S, what is the standard value? We can assume it to be 1000 kg per meter cube and rho S as 1025 kg per meter cube. We find that Z equals 40 times H. 40 times H means this depth of the interface below the mean sea level is 40 times the value of the height of the water table above the mean sea level. So that means the storage of this fresh water below the mean sea level is 40 times the storage above the mean sea level. It also means that if this water table, it goes down by 1 meter, what will happen to the interface? 40 times H. So it will rise by 40 times. Fine? But remember that this is not going to happen immediately. It might give you a very alarmist view of the situation, but it is not going to happen immediately. This might take a long time, and there are so many other factors which are existing in that coastal zone. But this is a thumb rule by which you can just make an estimate of the depth of the interface. Now, besides this regional problem, we also face the problem of local upconing of the salt water. What happens in this case? When we are pumping a well, and there we have the freshwater zone, and that zone is underlain by a layer of salt water. So when we start pumping from this well, what will happen to the salt water layer? When we start pumping, vertical gradients will get established below the well screen, and slowly this interface will rise. Once you stop the pumping well operation, what will happen to the interface that has risen up? It will again go down. So that means it will go down, but once you again start pumping, it will again rise. Now, initially, if you are pumping at a very low value, the rise will be small, but if you pump at a higher value, it will rise to a larger height. Ultimately, if you are pumping beyond a certain critical value of pumpage, this interface will become unstable and it will ultimately reach the well screen. And your well, which was basically giving you fresh water, it will ultimately start yielding saline water because your interface has reached the bottom of the well screen. Earlier, this interface was very much below the well screen, so your well was giving you fresh water. But now your well, the fresh water well, is giving you saline water. So this problem we faced in Andhra region of east coast of India, where the farmers, they complained of this kind of problem. So basically, we face two kind of problems in the coastal regions. One is the regional condition where the interface is intruding because of the pumping or recharge. Recharge will basically, it will help the interface move towards the seaward side, but pumping will aid the movement of salt water towards the landward side. So this is a regional condition. And what is the local condition? It is occurring at a micro level. Here, below well screen, we face the problem of localized uptake. So this distance between the well screen here, if you see, this distance between the well screen and the salt water layer, this is known as the cushion. Basically, it implies that if the cushion is more, it is thicker, the interface will rise and then it will fall. But if the cushion is very small, it is thin. So just a small pumpage will lead to the contamination of your freshwater well. So the planning issues, they involve, like if we are going for the groundwater development of a certain region, then the lowering in the water table, it disturbs the dynamic equilibrium and it results in the landward movement of the interface. So what are the implications? Implications are that the interface may encroach upon the screens of a few wells. That means the wells will fail because the interface has reached the well screen. But in some cases, what might happen? The interface has advanced towards the landward side. It has not reached the well screen, but there is a zone of heavy pumping. Earlier, because of the development which was not there, there was no saline water layer below the wells. But now, because of the interface intrusion, the well field is having a saline water layer. There's a cushion there, but still the interface has reached below the well screen. So that means if we want to go in for a sustainable development of the groundwater region, the coastal region, we can have two kinds of goals. One is at the regional scale, another is at the localized scale. Regional scale implies that we have to ensure a deep and short enough interface. That is, the interface should be much below the pumping wells, the well field, and it should be short. That means, okay, I don't have much time to show you. Are you able to understand, or you want me to draw something on the screen? Is it clear? Okay. So basically, the interface is short. That is, it is towards the seaward side. That means the wells are, you can pump out much water from the wells without drawing the salt water. So we have to ensure a deep and a short enough interface. But in case of localized planning, what we have to do, we have to design the wells and the pumping schedule so that we don't pump out the salt water. We are only able to pump out the fresh water, which is needed for us. So the large scale interface movement is caused by a large scale modification of the pumping pattern or the recharge pattern, and this is designed to keep the recharge, this design of the recharge or the pumping pattern, it is meant to keep the interface at a pre-assigned large enough depth. So basically, how can we design such kind of pumping and or the recharge pattern? We can use mathematical models to do this thing for us. Now, when we go in for mathematical modeling, you have to remember that fresh water and salt water, they are miscible in nature. They are not immiscible. So basically, it is a problem of variable density flow. What do we mean by variable density? The density of fresh water is less compared to saline water. But when they mix, the fresh water requires a different density because it has got this salt water. So it is a variable density flow problem. And it is one of the most complicated problems that we do in mathematical modeling. So here, it is the mathematical model for coastal aquifer. It involves the coupled solution of the partial differential equations. That means we have to solve the groundwater flow and we have to solve the solute transport equation, groundwater flow equation and the solute transport equation. So, and these have to be solved in an iterative manner because the density of the water is changing. This I will show you. But in mathematical modeling, we try to keep things simple as possible, without losing the actual reality of the phenomena. So here, basically the mathematical models that are in use, they are of two kinds. One is the sharp interface model, another is the miscible transport model. People also call it the diffusion transport model. So this sharp interface model, it is basically a thin transition zone model, wherein we assume that the interface is sharp in nature. So in reality, where can you apply this kind of model? Where the interface is not diffused. It is a thin transition zone. In such cases, you can, simplify your computation effort by assuming that it is a sharp interface. It is never a sharp interface, but here you can safely assume it is a sharp interface. So by assuming that it is a sharp interface, we have two flow domains. One is for fresh water and another one is for the salt water. So this is the freshwater flow equation and this is the saltwater flow equation. And what can be the model inputs? I hope you have been hearing lectures on modeling. So here we have forcing functions like the pumping recharge pattern, the initial heads and the interface, the boundary conditions and the flow parameters of the subsurface formation. What is the time?
45.
And the model outputs, they will give you the spatial and the temporal distribution of the fresh water and the saltwater heads at different advancing times. And you can use this equation to find out the elevation of the interface. Once you know the value of saltwater head and the fresh water head, you can compute the elevation of the interface. But here, what are the advantages and disadvantages of this kind of sharp interface modeling? It is very simple because not much of parameters are required. Simpler in terms of the computational burden also. And also in simulation optimization problems, it is quite easy to use a sharp interface model. But we have to remember it does not account for the diffusion or the dispersion phenomena, and it should not be used where the dispersed interface is thick. So this is a simple analytical equation, the Glover's equation, which will give you the shape of the freshwater saltwater interface under steady state conditions. So this is a very simple equation which we can use to find out the freshwater flow, which is occurring per unit length of the shoreline. So I will go slightly fast because not much time is there. And here again, we can find out the width of the submarine zone. We can find out the width through which the window, basically, through which the freshwater discharge is occurring into the sea. What is the depth of the interface below the shoreline at a certain point, and then the length of the saltwater wedge. This is your saltwater wedge. So this wedge, when it touches the impervious layer here, this is your length of the saltwater wedge, and this you can find out using the Glover's equation. So this is just to give you an idea that you can use simple equations also, but then here lots of assumptions are there. It is steady state in nature. It is homogeneous and isotropic aquifer. It is not a heterogeneous system, and also it is steady state. Then we have, besides the sharp interface models, we also have the different second category of models, which is the miscible transport models. Here we are simulating the variable density flow. As I told you, fresh water and salt water, when they mix, it acquires a different value of density. So here we are solving for variable density flow, and basically this kind of model has the capability to simulate the actual structure, the configuration of the interface, how the concentration of salt water is varying within the interface, that we can find out. So if it's a broad interface, we can very well find out the concentration values inside the interface. Now here we go in for the solution of the coupled groundwater flow and the solute transport equation. We can use numerical techniques like finite difference, finite elements, method of characteristics. And here what we do, basically we use the value of, the dependent variable in the flow equation is the pressure, because groundwater head and hydraulic conductivity, they are functions of density. So we use the pressure as a dependent variable here and the intrinsic permeability in the flow equation. So now don't get scared by these equations, because basically these days we have very good softwares which will do the job for us, but you have to understand what is happening in the, when you use this software, basically what the software is doing for you. So you have to first understand it and then you can use it properly. So this is the partial differential equation for the fluid flow, and this is for the solute transport. Here you see the dependent variable is your pressure, and we are using intrinsic permeability instead of the hydraulic conductivity. Why? Because intrinsic permeability is a property of the medium, not of the fluid. So here we are using the pressure is a dependent variable, and this solute transport equation, it gives you the value of the concentration at different spatial points. So here for this, okay, and here basically in the this kind of visible transport, what is happening? The transport is occurring because of advection and dispersion. So what is advection? Advection is basically the movement of the solute along with the bulk flow of the water, and dispersion is occurring because of the velocity variations inside the pores. So instead of being localized in a certain location, it will spread out, it get diffused. So this part is your dispersion, and this is the advective component in the solute transport equation. Now these two equations are coupled using this relation. Now here the specific rate or the density is a function of your concentration. So whenever we solve the flow equation and the transport equation, we use this equation to compute the new value of the density, and again we keep on solving. So we keep on solving the equation in an iterative manner. Now this job is done by a number of good softwares like CWAT. It is a very popular software which is used to solve these flow equations. Here the model includes, it again includes forcing function like the pumping recharge pattern. Here the initial conditions, they will include both the values of the concentration, the salt water concentration in your aquifer system, and the heads, besides the boundary conditions and the flow and transport parameters of the subsurface formation. And the model outputs, they will include the values of the heads and the concentrations at different advancing times. So basically this is a realistic simulation. However, there is a scarcity of the estimates of the different parameters which we need to solve the flow and transport equation. Also, it involves a computational burden in when we do the coupled management simulation optimization model. Recently, people have been using neural networks and genetic algorithms instead of going in for calling the simulation model again and again while using the optimization model. So that is another technique which people are using when they are solving the optimization problems. Now that this was at the regional scale, what do we do at the local scale? Local scale means when we want to manage the problem of salt water upconing. Here we need to skim the fresh water without drawing the salt water into your pumping well. So basically it deals with well design and pumping schedules, how the pump needs to be operated. So it mainly comprises of the well screen position. Why? Because we have to look at the initial cushion between the well screen and the salt water interface. What should be the duration of the single pumping spell, and what should be the rest period between two successive spells. So whether this pump should be shut off for 1 hour, 8 hours, 1 day, 2 days, that needs to be decided here. So that we can do using your simulation model. And then we develop the model for permissible limit of salt water concentration. Now you see, for irrigation, the TDS value that is permissible is up to 2000 milligrams per liter. So if your pumping well is drawing less than 2000 milligrams per liter, you need it for irrigation purposes, it's fine. So you can use your model to limit the extent of salinity in your pumping well. So again, if we use a sharp interface model, the limitation is that in reality, the transition zone is broad. So what will happen? Your pumping well will start pumping out the salt water much before then actually what the model might show you for the sharp interface. So it might start pumping out the saline water in advance compared to what is happening in the model. So, and this solution is not valid beyond a critical rise of the interface because the interface becomes unstable when we assume a sharp interface. So basically it's the numerical upconing models wherein we are assuming the dispersed interface which can provide you flexibility in terms of the well design and pumping schedules. So this is again a figure of the pumping well underlain by the salt water layer. This is your cushion. And when we start pumping, this is your drawdown cone. And in response to the pumping, this interface will start rising. So basically, we have to provide a sufficient cushion between the well screen and the rest position of the interface. This is your rest initial position of the interface. We have to provide sufficient cushion between the well screen and the interface. We have to restrict the pumping rate and the duration of the pumping. Both have to be limited up to a certain value. Then we have to provide sufficient rest period. Sufficient rest, time should be allowed between two pumping spells. If we keep on pumping or if we, stop the well, but the interface does not go back to its initial position, next time what will happen? It will start rising from this position. Next time again, it will rise higher. So we need to have a sufficient rest period between two pumping spells. So now there are other types of well configurations which we can employ to minimize the problem of saltwater coning. Here we can have a scavenging well or a recirculation well. Now these are compound well systems. I will just show you with an example. This is a scavenging well. Basically, this is a compound well system wherein we have two wells pumping side by side from an aquifer which is underlain by a saline water layer below the fresh water layer. And here, one of the wells, it is pumping out saline water from the salt water layer, and this well is pumping out fresh water from the fresh water layer. So what happens when we pump out the fresh water? This interface will rise, suppose, to this height. But when we pump out the saline water from this well, which is having the screen in the saline water zone, what will happen? This rise will be counteracted by the down coning of this interface. When we pump out the saline water, this interface, this will go down, this salt water interface basically. This will go down coning will occur. So this will get balanced out. So the total rise will be limited to this height only. Is it clear to everyone? I'm just trying to explain you the phenomena which is occurring here. So because of this pumping from the saline water zone, this rise of the interface is reduced. And this is the net rise of the interface. So this is your scavenging well. You are scavenging out the saline water and you can use it for some other purpose. And then this is the design of the recirculation well. Here again, this is a compound well system. We have two well screens pumping out water, and both the well screens, they are located in your freshwater zone. So here we are pumping out the water from the freshwater system, and this second well. Now here, this is having the screen towards the interface. So what we are doing, when we pump out the fresh water, we are putting a portion of this fresh water back into your well. So this is basically your pumping well and this is your recharge well. So when we pump out the water, upconing occurs, and when we put a little bit of water back into the system, it recharges your groundwater system and the net resultant is that the interface which would have risen by this height, the upconing gets reduced. So this is your recirculation well system, and this is your scavenging well system. Now the problem with scavenging wells is you pump out the saline water, but what will you do with the saline water? Can't use it. So this kind of technology is applicable where you are working near the sea coast. So it can be disposed of in some other setting. And this recirculation well, here the disadvantage is that you are losing a little bit of fresh water because you are pumping it back into your aqueous system. But basically, it is very effective in counteracting the problem of localized upconing. So we have been working on the development of such models, and because of the lack of time, I'm not able to show you all those things, but these are practically feasible solutions. So this planning of groundwater development in coastal aquifers, as you can see, it is quite complex in nature, and we have lots of local and regional issues, and the mathematical models of different types of complexities can be employed to plan the groundwater development. And whenever we go in for modeling, we require huge amount of data over a period of time, which is to be monitored. The data has to be monitored over a period of time, and then we can use it for the modeling purposes. No, okay, I will skip this. Now, I will just briefly focus on the management strategies. What can be the management strategies in a coastal aquifer setting? Basically, we can have three types of, three categories of strategies. First one is the monitoring, assessment, and modeling. Second is behavioral and institutional approaches. Third is the engineering measures. The first one involves the data collection and analysis, developing the database, and then scientific assessment and modeling. So modeling you have already seen, so I won't focus much on this. But this is the first strategy wherein we collect the data, we find out how the interface is advancing towards the landward side, and we have some objective in mind, and we do the modeling. Suppose we want to retard the movement of the interface, the advancing interface. So we can keep this as the objective to do the modeling for us. Then the second strategy is they focus on the behavioral and institutional approaches. Here we limit the amount of groundwater that can be extracted, or we can relocate the wells further inland. Now, if the well field was located quite near to the coast, what we can do? We can relocate the wells further inland. So that won't affect your water table gradients towards the landward side. Now, again, we can do some water saving measures, like we can reduce the amount of pumpage in that area by increasing the irrigation efficiency, or we can do some other kind of water saving measures, or we can go in for blending of water, like we can mix saline water and groundwater for irrigation purposes. Again, that will reduce the amount of fresh water that is being pumped out. So these are some of the behavioral and institutional approaches that can be employed in the area. Finally, we have the engineering measures. Now here, the effectiveness of these engineering measures, it depends upon the local conditions. So this is for the, when the intrusion is occurring through the surface channels, through the drains. So here, we basically physically prevent the salt water from entering into your drains during the high tides by constructing certain structures at the mouth of the drains. And what we can do for intrusion into the coastal aquifers, here we can have seawater barriers. Now, seawater barriers can be in terms of the subsurface barriers, low permeability subsurface barriers, and hydraulic barriers. We also have the technique of aquifer storage and recovery, wherein we inject the fresh water into the aquifer during the monsoon season, and then we can later on pump it out during the low supply seasons. Or we can increase the water table elevation. The gradient can be increased by recharging the fresh water on the inland side. Or we can use the skimming wells. Now, skimming wells, I've just explained to you, scavenger wells, the recirculation wells, or the partially penetrating wells. They can be used here. So these are some of the measures that you can employ, the hydraulic barriers. So these are the injection hydraulic barriers. Here what you can do, by using, injection well or a coastal canal, the water table gradient can be elevated to a certain height. So what will happen here? The water table gradient has increased. So it will not allow the seawater wedge to intrude beyond a certain point. So that means you can do pumping beyond this hydraulic barrier, that is on the inland side. But because of the presence of this high pressure ridge, it won't allow your salt water to intrude beyond a certain point. Agreed? Another kind of hydraulic barrier is designed using the pumping barrier. Here we simply keep on pumping out the water. Now remember, this is located parallel to the coastline, not at a single location. Parallel to the coastline, we can have a series of pumping wells. Now, whatever saline water is intruding into your aquifer system, it will get pumped out. So beyond a certain point, the water is being pumped out, saline water. So here, even if you are having a production well field, it won't allow it to go beyond that trench in the water table. So a sort of trench in the water table is being created. Now what might happen? You can't have your wells. Okay, let me just draw. There is no clock here.
No, you can continue for another 5 minutes.
Okay.
No problem.
So this is a coastline. And you have a series of a battery of wells which are pumping out the saline water. So what will happen? The salt water is not going intruding beyond this pumping well here. But in the space between the two wells, the interface might move into your aquifer system. So what we can do, we can create some injection wells here. Okay. So when we create some injection wells, it will create a pressure ridge, and whatever water was entering, it will be getting attenuated. So by having a combination, a battery of pumping and injection wells, you can manage the salt water intrusion problem. Lastly, what we can do, this is a costly in terms of economy, this is not a very economical type of strategy. You can use the physical barriers. So basically we have a concrete barrier here, and this will stop the movement of salt water. So you can keep on pumping out the fresh water, but the movement of salt water won't be there. But it is a very costly approach and not feasible everywhere. So the engineering technologies, they are very effective in addressing problems of the groundwater quality. Generally, these are site specific in nature. So the adaptation of the options of the scientific monitoring, assessment, and modeling, they are cost effective. You can know how the intrusion is occurring. You can do some modeling and take proper, apply certain strategies or certain measures to counteract the problem of intrusion. So in the end, I would simply say that this coastal aquifers, now the coastline, as I told you, it is a very important component which is contributing to the economy of our country. So but they present very unique management challenges, and by long-term monitoring, use of these models, mathematical models, knowledge of that area, the hydrogeology of that region, you can plan your development of the coastal aquifer system so that people who are residing there, they can get the fresh water supply. Otherwise, the supply is not pure in nature, it is not fresh in nature, it is saline in nature. So all those who are residing in coastal zones, they very well know the problem of salinity in the coastal areas. But this is how you can very well manage the coastal salinity problem. So this is a brief overview of the process that might be occurring in your area. We have been working in the coastal areas of Gujarat and also in Krishna Delta, that is in Andhra Pradesh. So one is on east coast, another is on west coast. So the problems, the hydrogeology is entirely different in both the region. East coast, it's a deltaic region. On the west coast, it's a hard rock region. Limestone formations are there. So, but it was a very, challenging scenario for us, and we were really lucky to have worked there. This is one of the photographs from the Gujarat high schools in the village, and we had installed one of our piezometers there, and whenever we used to go there for monitoring the levels, the data from the data logger, we were surrounded by hundreds of students. They were so enthusiastic, like what we are doing. So, better for their future, because they don't know the issues that they might be facing when they grow up. So that's why we need to plan the coastal aquifer development. I have not explained to you the field problems, the work that we have done, but this is a beginning for you. If you are interested in further taking up this in your research studies, this is the first step that you can take. Okay, thank you so much.
We have few slides on what you have done. Gujarat, if you have slides,
Yeah, actually, I had planned. Yeah, I had planned to keep it here, but then because of this 1 hour restriction, I thought that I might be already have intruded into the lunchtime. So I removed at the last moment. I removed it. Otherwise, I was really wanting to keep it here. Even this photograph, I placed it because it was a 4-year project that we carried out under the National Hydrology Project, this HP2 hydrology project funded by the World Bank. So in Gujarat, what is the problem? It is the state which is having the lengthy coastline in along all the coastal states. It is the Gujarat state which is having the longest coastline. So, and all along the coastline, there is a problem of saltwater intrusion. So, what people have done, the state government, in fact, it has been very active there. So, what they have done, suppose this is the Saurashtra Peninsula, and here all the villages, they are affected by salinity. So, they have taken several measures. First thing is they have constructed several adequate check dams. So, basically, this is the high, the land elevation is high on this side, and it is sloping towards the sea side. This is the sea coast. So, they have constructed check dams on all the small streams there. That has helped the water table to rise higher. Further, what they have done, they have constructed a spreading channel. This is a massive work that we took up, and all along the coast they have constructed a spreading channel, which is basically canal, and these channels are connected to small reservoirs. So whenever rain occurs, what happens? The runoff, the excess runoff, it gets stored in these channels. In the region where the rainfall is more, this channel will start flowing, and all these reservoirs, these are interconnected, and all over the coast, people are able to use this water for irrigating their crops during the non-rainy season. Again, the rainfall is not quite high here. It is a drought-prone region. So, people are able to use the water from the spreading channel. In addition, the spreading channel, it recharges the groundwater system all around the coast. So, basically, it is the infection barrier, hydraulic barrier that I was talking to you when I was telling you about the management strategies. So, this one. So, all along the coast, they have this spreading channel. So, the water table gradient, they are able to maintain it above certain height. So, it is helping in reducing the salt water content in the groundwater. Plus, in addition, people are able to use this water stored in the channel for irrigating the crops. So, over the years, when we monitored, we found out that the salinity has reduced to a certain degree, and the cultivation of crops that has increased. People are able to use it. So, the waste land that is getting converted into the rich agricultural land. And one more thing what they have done, like suppose this is river, we work in the Minsa River basin. So here, towards the coast, they have a wasteland where it is very saline. It is because of the geogenic inherent salinity in the subsurface. So what was happening earlier, when during the monsoon, the rainfall runoff was occurring, it was getting stored here in this depressed land. It is a grade area which is a very saline formation, and it is inverted saucer shape kind of thing. So here it was a depressed land. It was this fresh water runoff was getting stored here in the depressed area here, and this was basically saline in nature. So what was happening? Whatever fresh monsoon runoff was getting stored, the water that was having a potential for irrigating the lands, here it was getting mixed with the salinity, soil salinity. And as the months, like we go from the monsoon season towards the winter season and then the summer season, this water was getting mixed up with the saline soil, and it was turning saline because of the evaporation and the salinity in the soil. So basically, this water was getting wasted. Lots of water was there, but it was getting wasted. What the state government did? They sealed the mouth of the estuaries here. The estuary was there, so they sealed the mouth of the estuary using bandharas. In local language, they call it bandhara. So this bandhara is basically a wall which can be used to seal the mouth of the estuary. It is having a height 1 meter above the mean sea level. So whatever excess water is there, that flows out into the sea. But during the high tide, the sea water that you enter, now that is not spoiling your water stored in the grade area. So this grade area earlier, the water was turning saline because of the inherent salinity of the soil, because of the evaporation, and also during the high tides, it was getting mixed with the fresh water. So the high tide problem has been stopped. So now we have the saline water. Earlier it used to turn saline very fast because of the regular high tides which were occurring here. Now they are able to store the fresh water up till the month of February. The fresh water is there. So again, they have taken out some radial canals from this reservoir. Basically, this is a reservoir now. So they have taken out radial canals from this reservoir, and people are using this water to irrigate the lands. So all around the coast, you will find that the cultivation of crops has increased. So this is how you can actually use such kind of measures to improve the water quality of your post-factory system. So this is one example of how people have been working now. We have taken out a volume from post-factories with the Central Water Commission, and it has been published. It is there on the website. So different states, what measures they have taken in their own coastal areas to counteract this problem of salinity. Now this is a unique hydrogeological situation. This kind of measures can't be employed everywhere. In all the states, it's different. Like on the western coast, if you see the Kerala, Maharashtra states, there you have the topography is very steep. But on the eastern coast, if you see, because of Western Ghats on the western coast, the topography is steep. But on the eastern coast, what is happening? We have the big deltas there. So there the hydrogeology is different. So there are different kinds of measures can be undertaken. Here on the western coast, this is a different kind of strategy they are employed. So this is just a very brief overview of what we are trying to do in coastal areas in our country. Any questions? I would be glad to answer, or you can always contact me on my email. I hope you have understood and got a feel about coastal areas.
Yes.
Yeah? That's my gift. Okay, so thank you very much, and I wish you a very happy journey if you are going back today itself.
Thank you.